Hello, welcome to our lectures on object-oriented programming. In the previous lecture, we started building out a rational class that can represent fractions. And we started building up the functionality a little bit where we can create a fraction or a rational number. We can represent it as a fraction, and we can even reduce it into its simplest form. But currently, we can't do math with it. When we take a fraction, like 1/2, and try and multiply it by 4, we encounter a type error, unsupported operand type for multiplication, int and rational. Python is telling us it does not know how to multiply an integer against this new rational object we've created. We have to tell Python in our class definition how to implement these mathematical operators if we want to use them. And this is important because different objects may implement these operations in different ways. For example, 42 times 2 has a very different meaning from hello times 2. The multiplication for strings has the meaning of concatenation, whereas for numbers, it has the meaning of mathematical multiplication. So we have to tell Python, when we're defining a new object, how multiplication, or this star operation, should be implemented with respect to our object, and between our object and other objects. So if we look at the methods of integers, we find there are these methods, dunder methods, mind you, that suggest they have to do with arithmetic. We have add. We have, let's see here, pow for power. We have mul for multiplication, sub for subtraction, true division, div mod for modulus division. All kinds of functions or methods for performing arithmetic with integers. And just like repr is automatically called when we evaluate an object to construct a string representation, Python automatically calls these add, div, mul, sub methods for performing mathematical operations like plus, minus, star, and slash. So let's implement multiplication so that we can do 4 times fraction. So again, we'll have our init and repr method, and we'll define a mul method so that we can perform multiplication. And when we do multiplication, we multiply our object by another object, right? We have our, in this case, our number times another number. And what's happening here is we're essentially making a call, int mul 42 2. That's what's happening when we write out 42 times 2. So we have self for the object itself, that's calling the multiplication, and other, the other object that we will be multiplying against. So we have self and number here. It doesn't matter what we call this other argument, but it should be something descriptive. We expect to be multiplying our rational number by other numbers. So we'll call this number. And depending on what this number is, we might want to do different things. For instance, if that number is an integer, we'll want to return a rational number with the numerator multiplied by the number and the denominator effectively multiplied by 1. If the number is a rational number, we're going to want to multiply the numerators together and multiply the denominators together. And so we'll return a rational number with this numerator and denominator. And while we could also define how to perform multiplication for floats, for instance, we're going to leave off that part because it's a little more complicated. If we're multiplying by floats, we could get back a number that is not rational, or at the very least does not have a very concise representation as a fraction. It may require it may require a very, very large number in the denominator to adequately represent that decimal. So we're just going to for now, define multiplication for integers and other rational numbers. And the rest of our definition is the same as before. All we've added is this mul method. And once we define dunder mul, we're free to use that star operation to multiply together our rational number against integers or other rationals. So if we multiply 4/6 against 3, we end up with 12/6, which is what we would expect. 4 times 3, or 4/6 times 3 over 1. We can also do 5/9 times 2/3, and we get 5 times 2, which is 10, and 9 times 3, which is 27. So this is working quite nicely. However, we didn't provide any type of support for multiplying against floating point numbers. We just said that. So if I try to multiply a rational against a float, we get this type error. And in fact, we defined this type error up above. If number is not an integer or a rational number, then we trigger this else and we raise a type error that says expected number to be int or rational, got type of whatever this number is. So we expected number to be int or rational, got class float. We did not implement support for multiplication by floating point numbers. And that's not an unusual way to essentially define how the multiplication should take place between different types of numbers or data. You might break it out case by case, and then for everything that's not contained in the types of data you're prepared to handle, you just raise an error and say, sorry, this is not a valid input. Now, this could be a little bit more probably concise. We could probably say here, since we saw that integers, just like rational numbers, have numerators and denominators, we could have just here, just this for both, and it should work just fine. So that still works. So since integers in Python 3 have both a numerator and denominator attribute, we don't need two separate lines for handling ints versus rationals. We can handle them together in the same way. Now, one thing to keep in mind is this is the mul method of the rational object. When we write something like rational *3, Python is going to call the mul method, the dunder mul method, of the object on the left of the multiplication. If we were to try to do 3 times rational for 6, we encounter a type error because now we're calling the mul method of integer. An integer doesn't define how to do multiplication against a rational number. So if we wanted that to work, we would additionally have to define an rmul method. I believe this should now work. No, I need a self.mul like this. There we go. So in the event that multiplication is not defined for the object on the left, then Python goes looking for an rmul method of the object on the right. And since we define that to be equal to self.mul, the thing we just defined, number, it's going to do the exact same thing as if we had called rational *3. Now, the particular details of the fact that, like, oh, you also need to define an rmul method are not so important, because usually we won't necessarily be writing an object that needs to implement multiplication at all. You don't necessarily need that in your object. Most of the classes or class definitions that I've written do not contain any methods for performing arithmetic. Python and various Python libraries already provide us with an ample amount of objects for performing mathematics. So there's not a lot left in that space to contribute or add. Things like this already exist. In fact, in Python, there is already a fractions module with a fraction object for doing all the things I have been showing you. But it makes for a nice example, so we just pretend for the moment like that doesn't exist and implement it ourselves. What I do mean to highlight, though, is the fact that these dunder methods link into basic functioning in Python, and when we are writing new classes, we will frequently encounter them. Whether that's init and repr, like we might do for almost any object we define, or, for example, taking a look at the methods of list, equality for checking if two objects are the same, get item if we're defining a object where we should be able to index into it by position, len if we're defining an object that should have length. There's all sorts of dunder methods that may be very useful beyond the ones we've shown here for doing arithmetic. The arithmetic dunder methods are just very easy to understand, and doing arithmetic is familiar to everyone, so they make for a nice example. Also notice we've only defined mul at this point. We have not defined addition or subtraction. So if we wanted the full support for all kinds of arithmetic operations, we'd have to define quite a few more dunder methods. And defining classes can be a lot of work. We might have to imagine all the many ways we or other users might want to use an object. And we saw already for the mul method, we had to write some logic to handle the different ways in which someone might multiply a rational number with another number. So class definitions can get very, very expansive. For example, here we're eventually going to encounter pandas data frames, a tabular data structure. This is just the init method for a data frame. This is all just in the init method. You can see how long this is. And even then, it calls another class's init method at the end. That's a lot of code just for object initialization. But the reason is, as we look through, it has things like init mgr, init dict, and it's handling these different cases of the ways in which we might want to construct a data frame. All the different data structures we might construct a data frame from. Writing classes can be a lot of work. We will discuss in a subsequent lecture the idea of inheritance, which helps us break down that work somewhat by building a hierarchy of objects that share behavior so that we don't have to write out brand new code every time, but rather we can build up objects in the same way we might build up a composition of functions, where, for example, our getPrimes function relied on an isPrime function. The data frame here relies on another class called ndFrame, where a lot of the underlying functionality is defined. And it inherits that functionality from ndFrame. So we'll talk more about inheritance in a subsequent lecture. I want to highlight here, I already talked about kind of so-called private methods and dunder methods, but there is a section of text where those things are described here. So if my explanation earlier wasn't totally clear, you may want to read through this section of the notebook. I'm going to skip it since I already defined or described what those things are. So we're going to stop the video here, and in the next lecture, we'll talk about, we've described a lot of how to work with classes, what they are, but we haven't really motivated why we might want to work with classes, what the object-oriented perspective is, or how classes and objects relate to each other. So that'll be the focus of the next video.